So section 2.2 is going to discuss limits, and we want to investigate limits. We're going to investigate them several ways. So let me write that down here for you. We're going to investigate limits numerically, graphically, and algebraically. All three of these should say the same thing about our limits. Of course, I haven't really discussed what the limit is yet, but we will get there. Let's start by investigating perhaps a slightly more familiar function. Look at y equals 1 over x minus 3. Is this graph going to have a problem anywhere? Where at? Yeah, at x equals 3, we're going to have issues, right? Because you're going to be dividing by 0. So it's reasonable to expect that we're also going to have issues with other graphs where you divide by 0. Now let's take a look at this graph in particular right here. Y equals 1 over x minus 3. And you can kind of see what is a characteristic behavior where you have 0 in the denominator, that you have a vertical asymptote. So the line x equals 3 is approached from the right towards positive infinity, from the left towards negative infinity. But you can see that this graph definitely has issues at that point. So let's turn our attention to one of the problems in the book, which you might expect is going to have similar problems. So let me switch over back here. Problem number 2 asks you to calculate the limit as x approaches 0. And there's a little positive. No, actually, no, there's no positive. Sorry, my bad. No positive there. There we go. X approaches 0 of the square root of x plus 1 minus 1 over x. And they give you a little table of values that they want you to plug into. So we'll do that. We'll check it out using that table. We'll check it out numerically. Now, what do you expect, though? We expect, kind of looking at this, we expect behavior like we had up here, right? You have this vertical asymptote, because after all, you're dividing by 0. Well, let's see what happens. So what I'd like you to do is take out your graphing calculators, and we're going to make an adjustment to your calculators, a setting that we'll only have to do this once, but it's a useful setting. So what I want you to do is I want you to hit the second button and then the window key. Now you should see a menu like this. And what I want from you is to go down to the line that says independent, cursor over to ask, and press enter. Now if yours is already like that, that's great. Now your dependent, leave it set at auto. And what this is going to allow you to do is create tables of values and choose the values that you want rather than letting the calculator choose the values that you want. Now let's put in the function into your calculator. Let's put this into a calculator rather than having to calculate these things manually, which would be a real drag. So hit the y equals key. Let me clear out anything that's there. I'll show you 2 different ways you can input this. One is the general way that most of you should be able to do. So we'll put a left parenthesis, because we want to put all the numerator together. Left parenthesis, second, and then hit the square root key, second x plus 1. Now on my calculator, I've got to hit the right arrow key to get out of the square root. And then I'll hit the minus 1, and then a right parenthesis, divided by x. And that's great. That's fine. For those of you with a fancier calculator, with a TI-84 Plus, and you've got what's called Math Print, then life can be a little bit easier if you do this. If you hit the alpha key, then the y equals key, it gives you a menu of fractions. And that's kind of handy because then it means you don't have to be as careful and fuss around with parentheses. So I'll do a fraction, and it looks a little bit more like what I would write on a piece of paper rather than type into a computer or a calculator. So it's just a little more user-friendly. If you've got that, great. If you have a TI-84 and you want some help on that, then let me know. What we want to do next, though, is we want to go over to the table function. And if you have anything here, like I do, then hit the delete key, clear all those things out, and let's type in the values that they suggest here. So for number 2, they start out by suggesting negative 0.1, and then negative 0.01, and then negative 0.001. Now what's happening to these values of x? How would you characterize their behavior? They're getting smaller. And they're getting close to what? Yeah, they're getting close to 0. Let's try that from the other side. And if you notice, from the other side, they've got a similar set of values that are just positive, but again, approaching 0. They've got 0.1, 0.01, and 0.001. Maybe I should have put that in a different order. 0.001, 0.01, and 0.1. All right. Let's look at the decimal values that we have here. Are these decimal values blowing up? Is this ratio going towards positive infinity or negative infinity like it did near x equals 3 for that first example? No. It looks like these values are settling down near something, right? What value in the y column are these things getting close to? It looks like they're getting close to a half, right? Which is a little bit surprising. Based on our first example, we expected that we'd see some kind of explosion of values. We expected behavior getting close to positive infinity. So let me discuss a few things here about this notation. So this part right here is read as x approaches 0. So as x approaches 0, what's happening to the function? Well, what's happening here, the result of this is going to be your y coordinate. It's going to be where the y value is going. And in this case, it appeared that our y value is going to 1/2. So that's our limit. The limit as x approaches 0 of this function is 1/2. Now I promised to look at this a couple different ways. I promised to look at it 3 different ways: numerically, graphically, and algebraically. So this is the numerical approach. And it says that we're going to 1/2. Are you okay with that conclusion? Let me pull this back up here. So from either direction, from the negative side or from the positive side, the y values are getting closer and closer to 0.5. Now the graph doesn't actually have to be, or the function doesn't actually have to be defined at 0. It's just what are you getting close to as the values of x get close to that. So we're okay with our first conclusion. Let's take a look at this graphically. So it takes a little bit more finesse to show this on the graphing calculator, but I think I should be able to show it here pretty good. So I want the square root. You can highlight the keypad here to get the square root. Square root of x plus 1 minus 1. And let's highlight all of this. Then I'll divide that. So divide by x. Okay. So we want to see what's happening near x equals 0. Let me zoom in a little bit. And here's a set of coordinates. So it's giving you the same kind of limit values. But wait a minute. At 0, it's undefined. Okay, no shocker there. You can't actually put in 0 itself. But you can get as close to it as you want. And take a look at the y value. So as we come from the left or we come from the right, what y coordinate am I getting close to? I know it's a little obscured by the graph. Tell you what, let me shut it off real quick. What y value am I getting close to? 0.5. Yeah. So graphically, we're seeing the same thing that we saw numerically. That as you approach from the left or you approach from the right, the function is still getting close to that value. So that's the limit. So there it is graphically. So graphically, it's approaching 1/2. Now there's one last thing we need to do, and that is look at this thing algebraically. Hopefully it says the same thing. Hopefully we get the same conclusion. Now up here, if you try and put in a 0 into the function, what would happen? What would happen if I just tried to plug in the 0? Yeah. I get 0 divided by 0. 0 divided by 0 is undefined. We don't have a name for that. So we're going to have to do something else, a little bit more clever, to see if we can't figure that out. So what I'm going to do is I'm going to first rearrange this function a little bit. And my only trick in rearranging that is to multiply by 1. So how am I going to multiply by 1? Well, I'm going to use something that you haven't seen in a little while since you did your algebra work. But there's a nice little trick here, something that happens when you multiply a minus b times a plus b. Plus b. So a minus b times a plus b. What's the product of two things like this? A minus b times a plus b? Does anyone? Thank you. A squared minus b squared. So that's going to be my trick. Lining things up here, what's my a going to be? Yeah, square root of x plus 1 plus 1, right? So all I did was I changed this sign from negative to positive. I'm multiplying by effectively the conjugate. Now I got to do the same thing in the numerator and denominator. And here's where we're going to be a little bit clever. I'm not going to FOIL this all out. I know that when I FOIL this out, I'm going to get a squared minus b squared. What's a squared going to give me? X plus 1. And then give me a minus b squared. What's b squared going to give me? 1. Good. Now in the denominator, I'm not going to distribute. I'm going to leave this all together. Just leave it as x times quantity x, square root of x plus 1 plus 1. But something nice happens in the numerator, right? What happens in the numerator that's helpful? Yeah, perfect. The 1's cancel each other out. You're left with x over x times square root of x plus 1 plus 1. And now we can say ole here, cancel out the x's. So we're finally left with an equivalent expression, 1 over the square root of x plus 1 plus 1 again. This is an equivalent expression to what we started out with. Now, why did I do all that? Well, let's take a look now. Let's go back and look at this thing algebraically. we're going to look at the limit as x approaches 0 of the square root of x plus 1 minus 1 over x. That's equivalent to the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. In this first incarnation of this problem, you can't plug in a 0 because it gives you 0 divided by 0. But how about here? What if I plugged in a 0 here? Yeah, I get 1/2. So there you go. Algebraically, numerically, and graphically. All three of them are telling you the same thing. And in every single problem you do, that should always be the case. That you should always get the same thing no matter which approach you take. So we're going to do a bunch more where we're going to investigate things in multiple ways. But this was just the first. How are we looking on problem number 2? This is kind of like your intro to this stuff here. Yeah, please. Wait, up here? Oh, well, it becomes square root of 1. So this is square root of 1 plus 1. Square root of 1 is just 1. Yeah. All right. Appreciate the question, though. Anything else? Okay. Let's try another one like this. Yeah. So, did you want help inputting it or something like that? So what I suggest, kind of the safe way, is just use parentheses. You need to put parentheses around the entire numerator. When you enter this, make sure that you move past the square root, so you hit the right arrow, so that it only takes the square root of x plus 1 and not the minus 1. All right? Yep. Let's look at problem number 4. This one we're going to look at numerically and graphically. So we've got the limit as x approaches 0 again. Now, not all our limits are going to go to 0, although that certainly will not be uncommon. Limit as x approaches 0 of cosine of x minus 1 over x. Let's look at this one. All right, what do you want to do? Graphically first or numerically first? We'll do graphically first. So, again, we need to enter the expression into our calculator. There's one thing I want you to do before you enter that expression, and it's while I'm thinking of it. Make sure your calculator is in radians. Now, the fancy ones that I've been loaning out will show you if it's in radians or degrees. But if you're ever stuck and you need to change it, hit the mode key, go down to the line that says radians, degrees, and press enter with the cursor on radians. So calculus is done in radians. It's something you're going to have to get pretty used to. Sometimes you can get quite the wrong answer if your calculator's in the wrong mode. All right, so press the y equals key, and let's enter in our new expression. So I'll just clear this stuff out. Let's clear this stuff out, and do you like the trick where I use the fraction, or do you just want me to use parentheses? What works for you guys? Fraction. So you hit the alpha key, then the y equals key, and type the number 1, or simply press enter, and now you can just enter this as a fraction. So I want cosine of x, right parenthesis, you need to close that off, minus 1. Hit the down arrow key to get down to the denominator. And now I want to graph this thing. I want to figure out, well, what does its graph look like? So we're going to do a little bit of setup on the window. Now, where are we taking our limit to? What do we want our limit to go to? 0. What I strongly suggest is that you have a window that's set up with 0 at the center. Now 0 is at the center of this, but I don't really want to look at the function out at negative 15 and at positive 15. I want to look at it closer in. So let's go from, say, negative 1 to 1. Now that's on the x-axis. Where do you set up on the y-axis? Hard to say. So let me show you yet another trick on your graphing calculator. We're going to let our calculator do the work. Let your calculator set up the y-axis. So hit the zoom key, so in the middle there, and you want to hit zoom and then 0. Zoom 0 is zoom fit. And what it'll do is it'll adjust the y coordinates to fit your x coordinates. So you press zoom fit, and it should give you something that looks like this. Actually, I expected something different than that. Let's see, window. You know, I must have pressed the wrong one. Yours probably look zoom 0. There we go. All right. Does this look like what you got? No? Really? What's wrong? Y equals cosine x minus 1. Graph. Did you guys hit zoom 0? Really? And it looks different? Does anyone? Oh, you know what? It changed over my graph. Oh, I'm doing from negative 6 to 6. So negative 1 to 1. Zoom 0. Okay, I'm not sure why I made that initial change. I think I had a decimals or something like that on the first one. All right, there we go. Let's look at the graph near x equals 0. And you can see if you come in to the left of 0 or you come to the right of 0, what's happening to the y coordinate? Where's that y coordinate converging to? 0. Yeah. So that's the limit here. At least that's the limit according to the graph. So this limit is 0. Now the nice thing about your graphing calculator is that if you hit the trace button, you can trace around, you can see some coordinates. But if you try to trace all the way down to 0, what's the y coordinate at 0? It's undefined. You can't actually put in 0 into this function, but you can get as close to 0 as you want. And getting as close to 0 as you want, the y coordinate is getting closer and closer to 0. So it's not what's actually happening at this point, it's what's happening near this point. That's what the limit is. So that's a look at it algebraically. Let's take a look at, or not algebraically, let's look at it graphically. Let's take a look at it with numbers. In fact, the numbers from our previous problem should still work pretty good, right? Because we again had the limit as x approached 0. So let's go back over to our table, hit the second key, then the table function. Let's take a look at these y coordinates. 0.05 roughly, 0.005. What's this? 5e negative 4. Thank you. 5 times 10 to the negative 4th. So 5 times 10 to the negative 4th. So that means the decimals here, I need to move this 4 places to the left. That's going to give me 3 leading zeros. So essentially what's happening here is every time you add another 0 here, I'm getting another 0 here. These numbers are getting really, really small. They're getting close to what number? 0. So numerically, you're seeing that this limit goes to 0, and graphically we saw that this limit goes to 0. Now the actual proof of this, kind of a more algebraic or calculus proof, is going to have to wait a little while. But for now, I think that's pretty conclusive. One thing that I'd like you to be able to do is come up with your own values here. It's a question that I often ask on an exam, is you choose some values of x, and then fill in a table that shows me a limit is going someplace. And it's not all that hard. All you have to do is choose a sequence of values that are getting progressively closer to this number, whatever that happens to be. How are we doing on the first two examples? Doing all right there? All right, good, good. Let's take a look at problem number 12 then. So the limit as x approaches 2 of x divided by x plus 1 minus 2/3 divided by x minus 2. Okay. The first thing you should always do when trying to evaluate a limit is to try plugging in the limit. See if it works. If it works, great. I mean, it did in problem number 2. When we reformulated it, we plugged in a 0 and we got 1/2. It worked great. But it's not always going to work out. If you plug in a 2 here, we get 2/3 minus 2/3 is 0. 2 minus 2 is 0. You get 0 divided by 0. So it doesn't work. So you're going to have to do something different. You have to do this either algebraically or numerically. I mean, you have to reformulate it to do it algebraically, do it numerically, or graphically. So take your pick. Which one do you want to work on? Which way do you want to do it? Numerically? All right. So let's enter this into our calculator. So again, I'm going to use that little trick here, alpha, and then the y equals key. That gives me a nice fraction. I could do another fraction because I do have another fraction beyond that, but I'm not going to. So I'll do parentheses. Let's see, I don't need parentheses. I'll just do x divided by parentheses x plus 1 minus 2 divided by 3 over x minus 2. So that's our function. If you don't have a graphing calculator that has this capability, or you don't have it turned on, then this is how you can put it in. You do a left parenthesis x divided by parenthesis x plus 2 minus 2 divided by 3. A right parenthesis, now this closes off the entire numerator, and divided by parenthesis x minus 2 in the denominator. So it's a cool feature if you can get that. It's x plus 1, thank you. It's a cool feature if you can get this working on your calculator. All right. I'm just going to shut this off here. And let's go up to the table function. Let's see. All right, it's giving me decimal, or it's giving me fractions here, which is annoying. I don't want the fractions. If you don't want the fractions, you can hit the mode key and ask for answers in decimals. I think that'll be a little bit easier for us. So mode, probably could. All right, these numbers here are no longer any good for us. What limit are we approaching? 2. So we need to choose numbers that get close to 2. Now, we can't put in a 2 itself. If you put in a 2 itself, you're going to get an error. It's not defined at 2. But you can come up with a sequence of values that are getting close to 2. What would be a sequence of numbers that are getting close to 2? 1.9. Yep, 1.99. 1.999. Now that's getting close to 2 from the left side of 2 as you look at the number line. How about getting close to 2 from the right side? 2.1, 2.01, 2.001, etc. Does anyone recognize the value that we're getting close to? It's not really a very common one, unless you're pretty close to. Let's do one more. 2.0001. Does anyone recognize that fraction? 1/9. 1/9 is 0.111111111. So, now I'm not going to give you anything tricky like that to expect you to recognize it. And indeed, we can do this one algebraically. But that's getting close to 1/9. Okay. Do you want to work on it algebraically? Do you want to see a little bit more conclusively that that's actually going to 1/9? I mean, it's nice here. You could also take a look at the graph, but again, we need to reformulate this a little bit so that you can see that it's going to 1/9. So we can actually just plug in the limit and have it pop out 1/9. Now, the trick in this is that we've got what's called a complex fraction. And in particular, what makes this a complex fraction is you've got a fraction within a fraction. And we don't like that. So to clean this up, I'm going to multiply both the numerator and denominator by the LCD of these secondary fractions. So I'm using the blue there to denote the numerator and denominator of the primary fraction. We're going to multiply everything through by the LCD of these two to help clean things up. So it's going to look like this. X times x plus 1. No, just give me not. X plus 1 times 3. Sorry, my bad. So that's going to multiply both the numerator and the denominator of my fraction. And notice that this divided by this is 1. That cancels, it's 1. But instead of canceling it, what we're going to do is we're going to distribute it. It's going to multiply each of these terms. Now, as I multiply this times this, the x plus 1 is going to cancel. What will I be left with? 3x. Good. When I multiply this times this, the 3 is going to cancel. I'll be left with minus 2 times x plus 1. All right, let's keep going. 3 times x plus 1. I'm going to leave this factored in the denominator. Let's distribute the minus 2 and see what happens. So minus 2x minus 2 over 3 times x plus 1 times x minus 2. Is there some simplification I can get in the numerator? Anybody? Yeah. The x's here cancel, so I'm just left with x minus 2 over 3 times x plus 1 times x minus 2. And wow. Now I get some nice and much needed cancellation. Now I get 1 over 3 times x plus 1. That's what I wanted, and that's what I needed. So I needed to get rid of this x minus 2 term down there, because that x minus 2 term was what was causing me the problems. Okay. So let's rewrite this then. This is going to be the limit as x approaches 2 of x over x plus 1. You don't have to rewrite it quite like I am, but I'm giving you a complete picture. And we replace this. We replace this with the equivalent limit as x approaches 2 of 1 over 3 times x plus 1. What's the huge benefit in working with that second one? Yeah, you can plug it in. You can plug in the 2 And what do we get? 2 plus 1 is 3. 3 times 3 is 9. You're left with 1/9. And that's what we saw numerically. It looked like 1/9, 0.11111. We didn't recognize it at the time, but there it is. You can see that on your calculator is 1/9. Okay, how are we looking on that one? All right, pretty conclusive there. All your different limits should match. Numerically, algebraically, and graphically. They should all say the same thing. If they don't, there's something wrong. They should all say the same thing. Okay, let me give you a couple to look at graphically. And I want you to discuss them with a neighbor. So those would be problems 18 and 20. So let me zoom in a little bit. So these are in the book. These are a couple problems graphically. I want you to discuss them with a neighbor. And I do mean discuss with a neighbor. I know some of you are like, I don't want to talk to him. Please. At some point, you're going to get out in the working world and you're going to actually have to relate to other humans. So work on it now. Build those skills now. But try and calculate these two limits. See what you can come up with. I'll walk around. Mimi will walk around. We'll try and help out a little bit. So what you're trying to figure out is, where is the y-coordinate going? As I approach this number on the x-axis, where is the y-coordinate going for that function? The answer to that is your limit. So figure out where the y-coordinate's going, and that's your answer. The idea is not to do these on your calculator. The idea is to just kind of look at them and figure out what it is from there. I mean, you can do one of them on your calculator. I think most of you would probably struggle to put the other one in your calculator. All right, I don't hear a whole lot of discussion. Come on. Or is this kind of like, I'm confused, how about you? Yeah, I don't know what's going on. Where's the y coordinate? As you get close to that one's a little bit tricky. Problem 20 is a little bit tricky, maybe. Okay, so let's work on both of these. The first one, as x approaches 0, doesn't matter which way we approach 0, right? What y value are you getting close to for the secant? 1. That's it. That's all there is to it. Is what y value are you getting close to? 1. So equals 1. Now, a little bit trickier because you got this extra point, but it's the same idea. As you get close to, not as you actually put in the value, but as you get close to x equal 1 from either direction, what y value are you getting close to? 4. Now, the fact that the function has a different value here, it's actually at 2, doesn't make a difference to the limit. What counts is what you're getting close to. And as you approach from the right or as you approach from the left, you're getting close to this value of y equals 4. So a little bit tricky on that second of these. But it emphasizes something that's an important point with these types of graphs. Is you're not worried about the value of the function itself. It's what are you getting close to. Let's do a couple more from this section. Problem 22. Now, this is a little bit of a problem here for us. We're approaching x equals 0. There it is. X equals 0. Now, as you approach x equals 0 for this function from the right, what value of x are you getting close to? 2. If you approach from the left, what are you getting close to? 0. In order for this limit to exist, the limit from the left and the limit from the right have to be the same. So this one just doesn't exist. D and E does not exist. All right. The limit from the left and the limit from the right have to exist and be equal. All right. One last one here from this kind of stuff. Problem number 24. This time we're approaching pi over 2. I want you to come up with a conclusion. Here's pi over 2. See if you can't come up with a conclusion for this limit. All right. Volunteer. Someone. All right. Infinity. What did you get? All right. Well, it's all right. Approaching from the right of pi over 2, you're getting close to negative infinity. Correct? As you come in from the right. As you come in from the left, what are you approaching? Positive infinity. Do those two things equal? No. So yeah. So if the limit from the left and the limit from the right are different, then the overall limit doesn't exist. Those two things, they have to be going to the same thing. This is just like problem number 22 in that sense, that the limit from the left and the limit from the right are different. So the answer to problem 24 is just like the answer to problem 22. It doesn't exist.
Could infinity be an answer, though?
Yes. Yeah. If so. Yeah, let me give you an example of one where that could be the case. In fact, let's go back and take this one and modify it a little bit. Let me put parentheses around that and square it. So let's take a look at this one now. Wait, no, the square should have been in the denominator, not the numerator. Square. There you go. So Now, I might be a little bit different than some of my colleagues and authors, but to me, the limit is here is infinity. Because as you come from the right, as you come from the left, both limits are equal, and they're both tending towards positive infinity. So in that case, for me, on my test, you can just write, yeah, this one's going to positive infinity. And that's fine. Yes? They might just say it just doesn't exist. They don't like necessarily using infinity as a limit all that much. But nah, for me, I'm pretty comfortable saying that's infinity. Yeah, thanks. Okay, let's do problem number 26. 26 is a good example. I put problems like 26 on exams. I like it for a variety of reasons. One, there's really not much calculation. So you're not going to make a mistake with calculation, and it really gets to the heart of your understanding. Do you understand what these limits are all about? So let me switch back over here. .cam. Perfect. Let's see if we can zoom in a little bit there. Okay, so it's asking you a lot of things. It's asking you, what's the limit as we approach -2? What's the limit as we approach 0 or 4? Now, independent of that, independent of the limit, they also ask you to find the value. What's f of -2? So let's see f of -2. We'll start out with that one. I'll give you a little bit of a head start. Is the function defined at -2? No. So it's undefined. So 26a, undefined. But b, look at the limits. The limit from the left, limit from the right. And do the same thing with c through h. See what you can come up with. Help each other out. This is one, we've done several examples. You should be getting comfortable with this. I don't know how to be more blunt than this, but this is the kind of stuff that I want you to know and understand. That in order for these limits to exist, the limit from the left, limit from the right have to be equal. And when they are, great, find that limit. All right, so I'll put in this pause note so that if you're viewing it at home, you can just fast forward until I unpause. But help each other out. Maybe you want to work around this one? looking at these, part B, for instance, what's happening to the y-coordinate as we approach from the left side of 2? As we're approaching negative 2, what's happening to the y-coordinate? Going towards negative infinity. What's happening to the y-coordinate as we approach from the right side of negative 2? Positive infinity. Are those going to the same place? No. So if they're not going to the same place, then what's happening with the limit? Yeah. So the limit as x approaches negative 2 doesn't exist because the limit from the left and the limit from the right don't equal. What about f of 0? Is the function defined at 0? Yeah. Now you don't want the hollow dot, you want the solid dot. And the solid dot is at 4, so f of 0 should be 4. But how about the limits? Limit from the left and limit from the right, are those going to the same places? No. So that's a D and E. Let's move on to f of 2. Is the function defined at 2? No, so it's not defined there. But what about the limit? As you come in from the right or as you come in from the left, what y value are you getting close to? A half. Yeah. And don't take out a magnifying glass. I'm not expecting 0.49 or something like that. Look, these are friendly. So 1/2. Good. F of 4. F of 4 is 2. That's the value of the function there. But what about the limit? As you get close to 4, where's that function going? Positive infinity. Yeah, that's where it's headed. It's positive infinity. All right. You're okay with problem 26? Okay. Let me give you some homework. So for homework, try 1 through 27. You can skip problem 25, or excuse me, skip problem 23. Let's see, did I skip 23? Yeah, skip 23. So for homework, section 2.2, 1 through 27, skip 23. That's just the odds. It's always just the odds. But section 2.2, it's on page 75 is where that starts.